I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on quantum theory and the wave-particle duality, talking about photons, Compton scattering, and the de Broglie wavelength. In this video, we're going to talk about quantum theory and wave-particle duality. We'll start with photons, then go into Compton scattering, and then talk about the de Broglie wavelength. First, we're going to start with photons. So a photon is a massless and chargeless particle of light or pocket of light, a quantum of light energy and other forms of electromagnetic radiation. Quantum just means the smallest amount of something. So this is the smallest amount of light, the smallest amount of energy that can be transferred. And the energy of a photon can be calculated by multiplying the frequency times Planck's constant. Now, the energy is directly proportional to its frequency and exhibits both wave-like and particle-like properties. So the energy of a photon can be calculated, as we said, with Planck's constant times the frequency, but we can use frequency equals speed divided by wavelength to substitute in. So the energy of a photon equals Planck's constant times speed of light divided by the wavelength, and we can rearrange that to show that the energy of a photon times its wavelength is equal to Planck's constant times the speed of light, which is a constant value. So the product of the energy of a photon and its wavelength are going to always equal the same constant, which is Planck's constant times the speed of light, which is 1.99 times 10 to the negative 25th joule meters, or 1240 electron volt nanometers. Now, the momentum of a photon. Using his theory of relativity, Einstein derived an equation relating energy of a particle to its momentum and mass. This equation is the energy relativistic equation, and the energy relativistic equation is the energy squared is equal to momentum squared times speed of light squared, plus mass times speed of light squared, and that quantity squared. Now, for a photon, which is massless, we don't need the mc squared quantity. Value is going to be 0 since a photon does not have mass. So we can rearrange this equation to solve for the momentum, taking the square root of both sides, and momentum is equal to the energy divided by the speed of light. Now we can multiply in the numerator and denominator by wavelength, and we know that energy times its wavelength, well, that's just going to give us Planck's constant times the speed of light. Well, now we have speed of light in the numerator and denominator, so we can cancel those out, showing that the momentum of a photon is equal to Planck's constant divided by its wavelength. So lambda, that's the wavelength of the photon in meters or nanometers. H is Planck's constant, which we know we have two values for depending on our units. And lowercase p, that value is our momentum of the photon. Now the rest energy of a particle, the same equation can be used that Einstein used to find the momentum of a photon. So we can use this for subatomic particles. The rest energy is only really applicable for small particles. Rest energy for large particles is not going to be enough energy to be measurable compared to everything else. So if we find the rest energy of an electron, E squared, using that same equation, well, if it's at rest, the momentum is 0. So that means that E squared equals mc squared, that quantity squared. So the rest energy, taking the square root of both sides, is mass of that particle times the speed of light squared. Now we're going to transition to X-rays. So this is a type of electromagnetic radiation. The frequencies are higher than ultraviolet radiation. The wavelengths are around 0.1 to 10 nanometers, and this just happens to be about the approximate spacing of solids at the atomic level. And the short wavelengths allow X-rays to penetrate most materials with relative ease. Atomic structures act like diffraction gratings for X-rays. So we have something called X-ray diffraction, which then forms negative images of structures of bones, DNA, or crystalline structures of metals or solids. So that's how we understand what the shape of DNA or bones, what those look like by using X-ray diffraction. Now, X-rays are produced when electrons are accelerated through thousands of volts of potential difference. Those electrons then suddenly stop by slamming into a dense metal such as tungsten. And this rapid change in energy causes the electrons to release this energy as X-ray photons. So this is how X-rays are produced, by accelerating those electrons and stopping them very rapidly. So now we're going to transition to Compton scattering, which is what all of this is leading up to. So if we have an electron sitting at rest, and that electron has a photon that heads towards it and collides with it with an initial frequency and initial wavelength, what happens is there's momentum that's transferred to that electron, and the two move off at different angles. So the wavelength increases for the photon, and the electron moves in the opposite direction down and to the right versus up and to the right for the photon in this diagram. And then we can mark those angles. We'll call the angle of the photon theta and the angle of the electron and the angle phi. Now, the collision is an elastic collision, which means that not only is momentum conserved, but energy is also conserved in this. So we're going to start by drawing an energy bar chart. So our system will be the photon and the electron. And in the initial situation, the photon has energy as well as the electron has its rest energy. And then the photon collides with the electron, transferring energy to it, which decreases the photon's energy but increases the electron's energy. So we can write our conservation equation: the initial photon energy plus the rest electron energy equals the final photon energy plus the final electron energy. We know that a photon's energy is just Planck's constant times its frequency, so we can substitute those equations in for the different frequencies. The rest energy of the electron, we're going to add that to the initial situation, which is going to be the mass of the electron times the speed of light squared. And then we're going to use Einstein's equation and solve for E by taking the square root of both sides. So we're going to get the square root of PE squared times C squared plus the mass of the electron squared times the speed of light to the fourth. Now we can substitute in, we know that the frequency is just the speed of light divided by the wavelengths. So this is going to be our conservation of energy equation to help us derive an equation for Compton scattering. Now we also know that momentum is conserved, but in this situation, not only do we have momentum in the horizontal direction, but we also have momentum in the vertical direction as well. So we're going to draw two momentum bar charts. So in the horizontal direction, we know initially that photon is moving with a momentum of Planck's constant divided by its wavelength. It collides, and then it moves in the horizontal direction and vertical direction. So the horizontal component is going to be Planck's constant divided by the new wavelength times cosine theta. Then the electron also has a horizontal component of its momentum. So we're going to add the electron's momentum times cosine of its angle, cosine of phi. Now in the vertical direction, since the photon's moving horizontally, there is no momentum to begin with. So 0 is going to equal the vertical component of the photon's momentum, which is going to be Planck's constant divided by its new wavelength times sine theta. And then since it's moving downward, the electron's momentum is going to be subtracted the vertical component, the momentum of the electron times sine of phi. Now we're going to use these three equations, the energy equation, our momentum in the horizontal and the momentum in the vertical, and the algebra gets very complicated for this video, so we're going to just know that we use systems of equations to derive the Compton scattering equation, which simplifies all the way down to a rather simple equation from these three very complicated looking equations. So the Compton scattering equation simplifies down to the change in wavelength of the photon is equal to Planck's constant divided by the mass of the electron times the speed of light times 1 minus cosine theta. So delta lambda is the change in wavelength of the photon in meters. And then we're going to use the value for Planck's constant. Planck's constant is 6.63 times 10 to the negative 34th joule seconds. And then we're going to use the mass of the electron is 9.11 times 10 to the negative 31st kilograms. And the reason we're using specific values is because the speed of light is in meters per second. So we need to use those values. So speed of light in a vacuum is 3 times 10 to the 8th meters per second. Now, the angle theta, that is the angle of deflection of the photon from the horizontal. So looking at the diagram, we have an initial wavelength and a final wavelength. So the y lambda prime minus lambda naught is going to equal the change in wavelength. Then the mass of the electron is just the mass of our electron moving down and to the right. Then the angle theta that angle is just between the horizontal direction and the actual direction the photon is moving after the collision. Now this value, h divided by m, mass of the electron, times c, this is a constant because none of those values are going to change, which is 2.43 times 10 to the negative 12th meters, or 0.00243 nanometers. And this is known as the Compton wavelength of an electron. And what the Compton wavelength of an electron is, it shows that the wavelength of the electromagnetic waves work best if the wavelength is comparable to this value. This is why X-rays work best with wavelengths ranging from 0.1 to 10 nanometers. Now, if the energy of the photon is too low, for example, visible light, the shift is negligible. There's not enough energy for it to be transferred to the electron to cause a noticeable shift. And if the energy is too large, for example, gamma rays, then the energy transfer does not scatter the photon. What happens is the photon actually absorbed into the electron, transferring all of its energy to the electron, so there's no scattering. Now, the wave-particle duality, the photoelectric effect and Compton effect proved that light has particle behaviors as well as wave behaviors, which was proven in Young's double slit experiment. So we know that energy can be calculated one of two ways, Planck's constant times frequency, or Planck's constant times the speed of light divided by the wavelength. And the momentum of a photon is Planck's constant divided by the wavelength. Now, Louis de Broglie postulated in his dissertation in 1924 that photons, since they both have wave and particle properties, then it's possible for all forms of matter to have both properties as well. So using the wavelength equals Planck's constant divided by momentum, we know that if it's matter, that momentum is just going to equal mass times velocity. So this equation is known as the de Broglie wavelength, where lambda is the wavelength of the particle, for example, an electron. So we're looking really more at subatomic particles for this wavelength. And the h we know is the Planck's constant that we've talked about many times in this modern physics unit. And p is the momentum of the particle, which is just mass times velocity. Now, de Broglie just had a hypothesis, but his hypothesis was proven 3 years after his dissertation by the Davisson-Germer experiment, where nickel was used as a diffraction grating for an electron beam, and the diffraction pattern formed, proving that matter has both wave properties as well as particle properties. So this is an introduction to quantum theory and wave-particle duality. I hope this was helpful, and I hope you have a great day and even better tomorrow. If you found this video helpful, click the like button down below, subscribe to my channel, Cavi Coaches, and follow me on Instagram and X @CaviCoaches.